And I'm Tsukagoshi, and I'm in the Tokyo Institute of Technology. Today, I'm in charge of the first 45 minutes and related to the mainly pneumatic control. And the second half of the 45 minutes, Professor Nabae will be in charge. Okay, so let me start the beginning part, the former part. Can you see the slide? Okay, and my main research is as follows, which is related to the bio-inspired food robotics. And this is the pneumatic actuator inspired by the earthworm. The diameter is only 2.6 millimeters, and it was designed aimed to insert in the branch, the lung. And this is the actuator inspired by the octopus. And it is composed of the soft gel combined with a shape memory alloy. And this one is the actuator driven by the water hydraulics, mainly for the estimating for the message device. And this one is the actuator to insert under the human body to so stretch the wrinkles on the clothes. And this is the actuator to assist the wrist motion. And those are the actuators to directly touch on the human body. Since the pneumatic actuator composed of the soft materials is very good compatible with the human body. So this kind of actuator is very promising to assist the human body motion or the stimulate on the human muscle. These parts are the mobile robot driven by the mainly pneumatics and oil hydraulics. And the characteristic of the fluid power is a very high energy with very narrow areas. So it is very so promising to insert under the very narrow areas with a very large propulsion force. Okay, so if you focus on the nature, for example, you can find many creatures taking advantage of the fluid powers. For instance, if you look under the sea or inside the river, you can find many creatures using the water. For instance, this is a squid. Squid can run away by spreading the spear from the nozzle. And it can also proceed or propulse by using the seawater pressure from the nozzle. This is a blowfish, and if it faces to the enemies, it is going to enlarge its stomach by intaking the seawater. On the other hand, if you search for on the land, you can find many creatures using the air pressure pneumatics. For instance, this is a frogs. Frogs is trying to swelling its throat or the cheeks to enlarge its own voice. As you see, some creatures living inside the sea takes advantage of the seawater, while some creatures living on the ground is trying to use the air pressure. This is the laws of nature. Meanwhile, if you are going to select from these two choices, how can you select the liquid pressure, or how can you select the gas pressure appropriately? I'll prepare the video to show you the differences between two. Here, the inside of the cylinder, the water is fulfilled. If the rod is pressed, the pressure increases, but the volume doesn't change at all. Here, the very large force is applied, but no volume changes. On the other hand, here, the inside of the cylinder, the air is filled. And if the rod is pushed, the volume decreases and the pressure increases. These are one of the big differences between the liquid pressure and the gas pressure. Then the right side is called incompressible fluid, while the right one is called the compressible fluid. Okay. Then let's consider the energy. First, let's begin with the energy of the liquid pressure. At the beginning, the one mass is put on the cylinder. And from here, the liquid pressure is applied. And the mass is raised at the height of the h. In this case, the potential energy, mass times the gravity times the height, will be set, as you see, okay? And this m times g can be replaced by the pressure times the cross-sectional area A. Okay? And this cross-sectional area A times H can be substituted for the volume inside the cylinder. As a result, the pressure times volume would be equal to the potential energy. This is very convincing, right? And here, this pressure P is expressed by the gauge pressure. And the gauge pressure is determined by the differences between the absolute pressure minus the atmosphere. Then it tends to be expressed by this way. Okay, next, this is a case of the liquid pressure energy. In the case of the gas pressure energy, how large energy is required to raise the height of the h? Equal energy is required, the same energy is enough, or less energy, or more energy is required? Let me ask you the question. Can you press the raise hand button? Okay, there are three options. Equal energy, less energy than the liquid, or more energy than the liquid. Please push the raise hand button among these three. Okay? Push the raise button if you think that the same energy is enough. Okay. So please push the raise hand button if you think that the less energy, smaller energy would be enough.
So sorry, Professor. They are not able to press the raise hand button because they are not on the.
Oh,
Yeah, because students are not in this meeting room. They are not able to
oh,
press
oh,
the
I
button.
see. Okay,
Yes.
okay, okay. I
So
get
sorry,
it.
Professor.
Okay, I'll answer that very quick. Okay, so please consider by yourself. Okay, I'll answer. Wait a moment. Okay. As you can imagine that if you push the rod, then the pushing energy is reduced to make it shrink. Therefore, intuitively you can easily imagine that the more energy is required. And if you express by using the mathematical way, this energy is requiring as the much more energy as it's shown in the green part. The blue part is the same energy as the liquid energy, while the green energy is the more additional energy to make it push up. Theoretically, the energy for going to make it push up is composed of the two parts. One is the energy to the power transmission energy, which is the same amount as the liquid energy, while the other part is the expression energy. This is the energy to make it so shrink. And actually, this part is accumulated as the heat energy. So if you push the cylinder, the inside of the air is raising as a part of the temperature. The temperature is raised, and this energy is accumulated. Next, if the two cylinder is double cylinders are connected, and here the both cylinder is filled with water. If the one part is pushed, what happens? Here, the one part is pushed, the other part is extended as the same stroke as it pushed. And if the both side is pushed, they are completely locked. This is another example or another characteristic of the incompressible fluid. On the other hand, here the inside is filled with air. If the one part is pushed, the other part is not always extended as the same amount of the stroke due to the compressibility of the air. Therefore, if these parts are pushed, they cannot be locked. This is another characteristics of the incompressible fluid and the compressible fluid. And here, I'll show you the characteristics or the focus on the characteristics of the compressibility of the air. And the air can be part of a kind of the soft cushion, just like the spring. So how can you make use of these characteristics? I will show you one example. This is a video showing the just after the very big earthquakes. In Japan, there are many big earthquakes, and maybe in the same way as your country too. And just after the earthquakes, the rescue parties tend to search the inside of the collapsed buildings. And due to the aftershock, it is very difficult to search the inside of the collapsed buildings. So, how to collect the information on the wrapped people or the collapsed building will be the very efficient task. This is another picture which happened in the Taipei. And as you see, the similar situation can be observed. And so, how to find out the victims, keeping the safety from the outside, will be the very efficient programs. And in the USA, not the earthquake, but terrorism happened. And the New York itself was attacked by the terrorism, and the first rescue robot was introduced at the time. This is a drain pipe, and throughout the drain pipe, uh, the uh, the robot is installed. And as you see that then the rescue parties are uh, tend to rely on the technology of the robot. And after this accident, many robotic researchers trying to develop a kind of the rescue robots to be useful for this kind of the accident. And the problem itself is that, as I showed you in the last picture, only the small space can be used. But if the robot size itself is small, it will be difficult to cross over the obstacles. So, keeping the very small size, how to traverse the large obstacles will be the very essential problems. Then, keeping the portable and the lightweight size, we tried to develop a very small portable robot to make it traverse the large obstacles. After considering the several mobile methods, we focused on the jumping characteristics. On the flat areas, it is supposed to roll efficiently on the surface, and if it faces to the obstacles, it tries to jump. And after landing on, it is expected to recover immediately. Of course, by using the camera or some sensors, it is required to search for the existence of the victims. As a result, we developed a kind of this kind of the jumping robot by using the pneumatics air pressure. It could jump the three times higher of its own size, and it could also jump again to the another areas. This is the structure of this robot. It is composed of the two wheels driven by electric motors, and in the middle of the body, the one pneumatic cylinder is contained. And this cylinder is kept perpendicular to the surface supported by these two orange legs. Therefore, even after on the rough terrain, it could jump again. And another advantage of this mechanism is that even though it can land on the upside down, it can recover immediately. Please show this the installed rope the legs. It can insert it in the wheels if it is pushed to one side, and it can react the force from the opposite side. Then just to so making things rotating, it can recover. This is a motion to the recovery motion. And it can also carry the speakers to collect the voices from the victims under the debris. Okay, the inside of the robot, it is composed of the following the components. This is a gas bomb, the CO2 gas bomb. Actually, it has 6 megapascal very high pressure. And this is a regulator to make it output the constant pressure. This is a PET bottle. This PET bottle plays a role as a kind of the tank. And by using this tank, it can supply to the valve. And by way of the valve, the air pressure is controlled. And then the cylinder is extended. So symbolically, these elements can be usually expressed by this way. This is a gas pump, the power pump, regulator, tank, switching valve, and the cylinder. And the question here is that how to make it jump as high as possible, limited by the pressure restriction. Can you imagine how to make it jump very highly? Of course, the pressure is high, that it can jump higher. But the pressure is limited, and if the pressure is raised much more, the much durable, the much high, the thick material will be required. As a result, the robot tends to heavier and heavier. And it cannot lead to improve the jumping performance. Then I will show you how to solve this problem. Before that, let us make sure the jumping process. This jumping process is composed of the 3 steps. The first, the cylinder case is extended. And in this case, it is followed by the motion formula. M1 means the mass of the cylinder tube, and V1 is the velocity of the cylinder tube just before it collides with the rod. And this is the pressure inside the cylinder. The pressure times the cross-sectional area means the force to make it go upward. And this term is a gravity term. And the T1 means the time between the beginning of the pressure applied and the end just before the collision. The K1 shows the friction. The next one is the colliding process. Here, the V1 is the collision just before the collision velocity, and the v2 means the velocity just after the collision. If you can imagine that in this process, the momentum can be preserved, then the momentum preservation can be kept. Then, using the velocity v2 just after the collision, as the third step, this kinetic energy, m1 plus m2 times the v2 square and half, is changes into the potential energy. Then the jumping height can be determined. Okay, so this is a question. If the volume of the cylinder between two is the same, which one can jump higher? One is the thin and longer one, and the other is the thick and shorter one. The volume would be the same. Which one can jump higher? I had the question at the time. And according to the first step equation, you can easily imagine. If you assume the inside of the cylinder pressure is kept constant, then you can assume that this first term is approximately the constant, which means the pressure times cross-sectional area A. This is the integration of the force related to the time. This can be almost the same. On the other hand, this gravity and the friction can be set to be the same, but T1 would be shorter if the cylinder becomes shorter and shorter, because the extension terms can be shrinked. As a result, this is the example of the simulation, and the horizontal axis shows the cross-sectional area, while the vertical axis shows the jumping height. Then, ideally, it follows this brown dot tendency, which means the shorter, the higher. If you assume that the pressure inside the cylinder will be the same, the constant. But actually, the pressure changes, the dynamically changes. So how can you calculate this dynamic change? This would be the next problem. To draw out the tendency, you need some knowledge related to the pneumatics. So I'm going to explain the basic characteristic of the pneumatics. I'm going to show you the 6 equations to draw out the dynamic pressure tendency. The first one is the first law of the thermodynamics. Maybe almost all of you know this tendency of the theory, which means the input energy into the cylinder changes into the internal energy and the outside work of the work to the outside by the cylinder. Okay, this is our first equation. The second one, the internal energy can be expressed by the temperature inside the cylinder. And more specifically, it is composed of the specific heat for constant volume of air. This is a constant term. And G expresses the mass inside the mass of the air inside the cylinder. And by using this equation, the internal energy can be estimated. The third term is the input energy to the cylinder is composed of the two factors. One is the energy to be supplied from the tank, and the other is the energy from the outside of the cylinder. And this is expressed by the coefficient of the heat specific times the temperature inside the cylinder times the changing ratio of the mass of the cylinder. And the other is a factor of the heat energy expressed by this way. The third one is how to change the air condition. It is considered between the situation inside the tank and the output from the valve. This is very high-speed change. So there is no room to be added by the heat energy. So you can assume that this change is adiabatic change. So no energy is supplied, then it is followed by this equation, which is called the Poisson formula. Then the pressure and the temperature here and here and here and here can be expressed by this formula. And this is the very famous phenomenon of the adiabatic change. If the PET bottle is pushed and released, the no room to be supplied to from the outside, so it's a kind of the adiabatic change. The inside of the PET bottle, water is contained. So the vapor is suddenly appears, and then it becomes white inside the PET bottle. And the fifth formula is followed by the ideal state equation, which means that the pressure times the volume is expressed by the mass and ideal gas constant and the pressure, the temperature. And this means that if the temperature is determined, the pressure, the volume situation condition can be also determined. This is also the expression of the energy inside the cylinder. And please make a notice that there are two ways of expressing the pressure, as I showed you last time. And generally, the absolute pressure measured from the complete vacuum is expressed by the big character, capital, while the atmospheric pressure is expressed by the small characters. It is called the gauge pressure. And if you're trying to use the pressure, I'd like you to imagine how large itself. Normally, for the pressure inside the tire in the of the automobile, the 1 kilogram force per centimeter square is the supplied inside the tire. And it is also expressed as a zero point 0.1 megapascal or 1 atm. And it is regarded as almost the same value as the pressure of the 10-meter depth inside the water. Additionally, I'll give you another information. And in the liquid, it follows this energy constant, the tendency, which means P1 pressure added by the velocity, the kinetic energy, is the almost the same, or not almost, but it is kept the same if the cross-sectional area is shrunk. By using this relationship, the velocity of the shrunk part can be expressed by this term, and it can be approximated to this value. Then according to this equation, you can say that the flow rate itself is proportional to the root factor of the pressure differences. Then this is a graph of showing the flow rate related to the pressure. This is pump pressure, and this is cylinder pressure. And if the pressure inside the cylinder equals to the pump pressure, no flow rate occurs. But following to the last equation, in the case of the incompressible fluid, it shows this, the traces this tendency. On the other hand, in the case of the air, it shows a little bit different tendency. In the same way, the horizontal axis shows the pressure ratio, while the vertical axis shows the mass flow rate. This is a border of the change tendency, almost half. And if the pressure rate is less than the half, the flow rate itself is kept constant. It is called the sound flow. On the other hand, if the pressure inside the cylinder becomes higher and higher, and it approaches to the pressure inside the pump, then the flow rate suddenly decreases. This tendency can be recognized as follows. If the second room, which means the pressure inside the cylinder, is small enough, then no reaction force occurs. Not large reaction force occurs. So large amount of flow can be supplied. On the other hand, if the pressure inside the cylinder is increased, then the reaction force tends to work on the pump. Therefore, it is hard to be supplied to the inside of the cylinder. As a result, the flow rate tends to be decreased. And this is the approximate equation, and it can be expressed by this way. So by using these 6 equations, we can estimate the dynamic change of the pressure. The horizontal axis shows the cross-sectional area of the cylinder, while the vertical axis shows the pressure just before jumping. As you see, the larger the cross-sectional area becomes, the pressure just before jumping decreases. You can recognize this tendency as this way. If the cylinder becomes the fatter and fatter, the changing ratio of the volumes is very large. So the flow rate cannot follow to this tendency. As a result, the pressure tends to decrease. So combining this tendency and the last equation, we can find out the jumping height considering the dynamic change of the pressure. Therefore, you can see that we can find the optimal cross-sectional area of the cylinder, which can maximize the jumping height. And so by using this tendency, we developed this kind of the robot. And it could jump 4 times higher than its own side, a little bit increased. And actually, so combining with some sensors, the optimal jumping timing would be calculated, and it could make it jump much higher. Here, the photoelectric sensors are installed, and if the sensor is turned on, it can automatically make it jump. Okay. And this project is stopped in 2008. The main reason is that the budget was also stopped. So we couldn't help but stop this project. But in 10 years later, some company in France focused on our project, and they tried to make use of it as a toy robot, amusement robot. This is not our actual dream, but the commercialized robot itself will be also enthusiastic for me. So we focused on this project, and they named it the Jumping Sumo. I'm not sure why they named it. And this is the motion of the robot itself. This is a much smaller robot, and containing the small camera, it could estimate where it is. And I'm wishing that combining with Wi-Fi and the internet, it could supply some information which is captured inside the private house. And just in the case of the emergency, this information is so communicated to the fire station or some other areas to rescue the victims' people in the future. Okay. Maybe time is coming. So I'm going to switch to Professor Nabae. But is it okay?
Yes. Can you see the slide? Okay. Yes, so
Yes, we can see it very clearly. Thank you.
okay, so I explained the pneumatic control system, and after that, I introduce the our research achievement as an example of a pneumatic control method. Okay, so I'm Hiroki Nabai, assistant professor of Suzumo Laboratory, Tokyo Tech. And my specialty is in actuators, robotics, and mechatronics. And I obtained my degrees from the University of Tokyo, and from 2015, I joined Tokyo Institute of Technology as assistant professor. So Suzumo Laboratory and Gendo Laboratory is collaboratively we have activities on the research top robotic research. And our field is very wide. So from the basic element like actuators and sensors, and from that kind of element to the field of test, like these robotic systems. And first, I will explain about the actual devices for pneumatic driving system. And after that, I will explain the examples of application using pneumatic driving them. Okay, so this slide shows the typical system for the mechatronics devices using electromagnetic motor. So I'm not sure all of you know well about this system, but the first microcontroller is programmed and generates the reference signal. And to send the reference signal to the motor drivers, and the motor driver controls the current or voltage to the actuators, and actuator can drive. And microcontrollers, when microcontrollers generate the output reference, so it uses information from the sensors or switches to know the environmental information. So basically, the configuration of the pneumatic driving system is same as the electromagnetic motor driving system. So first, you program the controllers, and the signal is sent to the valves, and the valves control the pressures or pneumatic flow to the compressors. And basically, compressor to pneumatic power is not directly sent to the valves. So first regulator regulate the compressors flow, and the regulated pneumatic power is sent to the valve, and the valve switch the flow of pneumatic power. And the controlled flow by the valve drives the actuators. So the compressor is generating the pressure. And there is some types of compressors. So these are examples of compressors. And when you choose a compressor, the flow rate and pressure range is important point to select which compressor is good for your system. The, so if flow rate is not enough, the motion is very slow. And if the pressure range is not enough, the, you cannot achieve the enough amount of force by the actuators. And the regulator is generally used to regulate the pressure from the compressor. And these are examples of regulators. The pneumatic valve is one of the important elements for pneumatic driving systems. These are typical examples of pneumatic valves. The upper part is a three-pot type pneumatic valve, and the bottom shows the five-pot type pneumatic valve. So these P and R means pressure pot and release pot. The pressure pot is connected to the pressure source, and the release pot is connected to the air atmosphere. And switch the connection here by switching the connection here, you can control the pneumatic pressure to apply to the actuators. The five-pot valve is a, works as similar, almost the same as three-pot type, but it can connect the two port to the actuators. So this slide shows the relationship between the actuator and the three-pot type pneumatic valves. So if you it is required to control the one part pneumatic pressure of one part of the actuators, the three-pot valve is enough. So connect to here, and if the pressure port is connected to the A port, the actuator, this part of actuator, the pneumatic pressure of this part of actuator increases, and the actuator go right side. And if the port A is connected to the release port, the pneumatic pressure decreases, and actuators go to the left side. And this slide shows a five-pot type valves example. So the previous example is using a spring to move to the left side. But this type of actuator doesn't use the spring, so it needs a five-pot type valve. So A port is connected to here, and B port is connected here. And if a pressure source is connected to A and the B port is released to the atmosphere, the actuator go to the right side. And if the connection is opposite, the actuator go to the left side. The next, I explain how to drive the valves. So basically, the controller like microcontroller send the reference signal to the valves, but generally the microcontrollers cannot generate enough power for driving the valve. So in general, it needs a driving circuit for drive the valves. This is the same as driving the electromagnetic motors. So this is an example of electric circuit for driving. So this is transistors and these are the resistance. And this is the voltage source. So voltage source means that the source, electric energy source, it can generate enough power for driving the valves. And from here, the microcontrollers apply the voltage as a reference. The transistor can control the electric power from the voltage source. The voltage or electric current is small. The current running through the bulb is small, and the voltage or current from the microcontroller is enough large. The current running through the load from the voltage source increase, and so bulb drives. I skip this slide. So basically, the normal bulbs can control the pneumatic pressure or pneumatic flow rate just on or off. It means fully open or fully closed. But so there's a very convenient device for control the pressure continuously. So electro-pneumatic regulator is one of the example for that kind of pneumatic control. So we can electrically control the pressure applied to the actuators by electro-pneumatic regulator. So if we generally, if we apply the reference voltage to the electro-pneumatic regulator, the electro-pneumatic regulator can control the output pressure according to the reference voltage signals. And the other important components for pneumatic driving system is shown in this slide. So hoses or connectors is very important to composing the pneumatic driving system to what can I say? So to send or connect the pneumatic pressures. And manual valve is also convenient for test or prototype the pneumatic driving system. And the speed controller is also convenient for test the pneumatic systems. It can control the pneumatic flow rate. And to design the pneumatic driving systems, it is very important to there is some critical parameters to consider. So for pneumatic pressure and flow rate and the response time of devices are very important to achieve the ideal performance of your soft robot. And uh, compose the electronic driving system of a component, input voltage, input power, or the range of voltage it can generate is very important to drive the pneumatic valve or some electric device for pneumatic control system. And from here, I will introduce the example of the pneumatic driving systems by my research achievement. So this slide shows the Markman type lever actuator. So very famous artificial muscle driven by the pneumatic or hydraulic input power. So the Markman rubber actuator mainly consists of rubber tube inside and sleeves of fiber outside. So when we apply the pneumatic pressure to the muscle, so generally it can contract. So, uh, so generally it can contract, but we can design to expand the expanding the length by applying pressure. It depends on the design of sleeves. And our laboratory develops the thin pneumatic artificial muscle. The principle of driving is completely same as the conventional magnet muscle, but the diameter is very small. So due to that very small diameter, it can show the flexibility, very high flexibility, even in the state of driving. And though by this flexibility, we can configure various type of configuration of actuator. So bundling with shapes or another shapes of configuration. So due to that high flexibility, we try to achieve the fabrics that can actively moving. So these active fabrics can contract. And using these active fabrics, we developed various devices, so, such as assistive orthosis and old fitting suit, comfortable corset, and soft grippers like this. And this is, I think, most famous example of this same magnet muscle applications. We apply same magnet muscle to muscle skeletal robot like this. So due to very small diameter and flexibility, we can densely install the actual muscle on the skeletal system like this. It can move, so very similar to the actual human. And we apply symmetric muscle on the neck and hand and the core like this. So this muscular robot can do muscle training like this. So in this system, we uh, use this kind of configuration of pneumatic driving system. So computer, the normal PC send us serial communication, the order but via the serial communication to the microcontrollers, and the digital data is sent to the pneumatic valves via the electric driving circuit. And the air pressure is regulated. Air pressure from the compressor is regulated by regulators, and solenoid valves switch or control the pneumatic pressure from the regulator, and those symmetric muscles is driven by the output of pneumatic pressure from the solenoid valves. Next example is a very long arm driven by this artificial muscle. So this long robotic arm is mainly consists of the thin artificial muscle and herring field balloon. So as you can imagine, when the length of a robotic arm increases, the moment or by the weight of body is critical for the motion of robotic arm. So our idea is that buoyancy force by the helium can compensate the weight of the body and decrease the weight of the robotic body. Uh, we would like to decrease the weight of the robotic arm as much as possible. So we use the axial muscle because it is it has a very small diameter, and also it it weighs very small. So this is actual prototype of the robotic arm. The length is 20 meters, and the joint number is 20, and it's very small, but the camera is installed on the tip of this robotic arm. So this is a movie of prototype. The helium gas is filled. The body is filled with the helium gas like this. And this is a view from the camera installed on the chip. By controlling the pneumatic pressure applied to the symmetric muscle, we can control the motion of the robotic arm. This is control view. The robotic arm will go into this hole. If we use a conventional robotic arm, it is very dangerous when robot is contact to the structure. But this robot is very lightweight and the body is very soft. There is no problem if the robot contact to the structure in the environment. So this is the pictures in the video. The robotic arm can go into this hole and succeeded in capturing the, this target. This. And when during the operation, the robotic arm contacted the structures like this, but there's no damage both on the robotic arm and structure around the robot. This is an image from the camera on the top, tip of the robotic arm. So this slide shows the pneumatic driving system of this long robotic arm. The PC is generate the data to data required to the motion, and via serial communication, the data is sent to the microcomputers. And the microcomputer generates the pulse width modulated signals. And this PWM signal is sent to the analog bulbs via the low pass filter to decrease the noise because of the PWM. And the power supply means the electric power supply to drive the analog bulbs. And the analog bulb means the electro-pneumatic regulator. And the compressor is connected to the these analog bulbs to supply the air source. And the analog bulbs control the pneumatic pressure applied to the actual muscles. And the camera installed on the chip of the robotic arm sends the video signal to the monitor. So we can check the view of from the chip of the robotic arm and control the motion of the robotic arm using the GUI like this. So next example is tensegrity robot. The tensegrity structure is the one of the unique structure often used in the robotic system. It is composed of the thread that generates the tensions and strut that can support the compressive force. So there are many types of tensegrity structures, and this is one of the typical structure of tensegrity structure. And there is a many tensegrity robot like this, but many tensegrity structures can the motion of many tensegrity robots is just rolling. Though our motivation is that if we achieve the more diverse movement of tensegrity robot, the applicability of tensegrity robot can increase. So this is our proposed tensegrity module and the robot using that modules. So as you can see from this video, the tensegrity structure can deform in a large with a large displacement. So this tensegrity structure is also driven by the same magnet muscle. It can achieve the large deformation for the construction motion and the extending motion. Five modules of these 5D modules are connected to compose this robot. So this is interval type locomotive robot. It can drive like this. So in a small so using the wall, it can locomote like this, and the robot also climb the vertical pipe like this. And this robot also goes through the curved path like this. So because of the softness or flexibility of the body. And this movie is on our YouTube channel, and we conducted a field test like this. The robot successfully going to move in the solid path like this. So this slide shows the pneumatic driving system for this robot. The compressor is here, and the regulator controls the flow rate, pneumatic pressure from the compressor. So 3-port pneumatic valve is used to drive the muscle in this driving system. The command signal is generated by microcontroller, and the signal is sent to these cylinder valves from the microcontroller. And, the pneumatic pressures controlled by these cylinder valves is sent via the pneumatic forces and the robot drives. So in the previous slide, we only show the contraction or extending motion, but we also achieve the bending motion of this tensegrity structure. The configuration of pneumatic muscle is same, but by changing the pattern of applying pneumatic pressure, we can also achieve the bending motion like this. And by connecting these modules, we can achieve this kind of robotic motion. The chip module is not a bending module, but the module for gripping the balls. And by extending the module, it can approach to the balls, and by gripper, it can catch the balls, and by bending motion, it can place the balls to the appropriate place. And we also try to achieve the torsion motion. The configuration of the pneumatic muscle is a little bit different from the bending and or the contraction modules, but the elements are completely the same. And by this configuration, we can achieve the plus minus 50-degree torsion motion. This. And by this torsion motion, we can achieve this kind of operation. So removing the caps of bottles like this. So this is the whole view. So by extending onto this module, it can approach to the bottle, and by gripping by this gripper module, and by torsioning motion, it can rotate the caps. And the combination of these modules, the robot arm succeeded in removing the caps from the bottle. The next example is giraffe neck robot. So as you know, the giraffe, especially giraffe neck motion, is very powerful, but shows the high flexibility. It is very good performance for the large scale soft robot. So we are mimicking the configuration of the real giraffe neck. So we prototyped the giraffe neck robot like this. So we install the simultaneous muscle on the skeletal model of giraffe. So these are these figures shows what part of muscle we mimic. So this movie shows the prototype motion. The flexion motion and extension we achieved. So this movie shows the lateral motion. So lateral motion is a little bit more difficult than the flexion motion. And the absorption is demonstrated by the previous movie. And this movie shows the interaction between the two giraffe necks robot. And this giraffe neck robot can show the shape adaptability like this. So this slide shows a sort of Japanese description. So this slide shows the pneumatic driving configuration of this giraffe neck robot. The PC generates the command signals, and this signal is sent to the microcontroller, and microcontroller generate the signals for the valves, and the electro-pneumatic regulator controls the pneumatic pressure according to the signals from the microcontroller. And by the pneumatic pressures controlled by electro-pneumatic regulator, the robot can drive. Okay, so we skip this one. Okay. next example is very special one. So previous examples using the pneumatic valves, but this actuator doesn't use pneumatic valves. So without using the pneumatic valves, it can generate the oscillating motion. So this actuator is composed of two parts, so fixed part and the rotating part. And when we apply the constant pneumatic pressure from here, the air goes through like this, and by the airflow here, the torque is generated in this direction. And when in this state, the flow path is connected like this. So the pneumatic flow goes opposite side compared to this state, and torque is generated in this state. So repeating this process, it can generate oscillating motion with constant pneumatic pressure. By using this actuator, we developed this flapping robot. It cannot support its weight itself, but it can generate the thrust force like this. So this part is rotating and shows the continuous oscillating motion. And by this oscillating motion, the wing oscillate and it can generate the thrust force like this. So it is very special and one of the, I think, good for the simple achieving a simple pneumatic system without valves. Okay, that's all. I think it's time to finish this class. Thank you for listening.